Hello. In this video we're going to take a look at the infinite potential well, also sometimes known as particle in a box. The potential is as follows. So 0 within the region 0 to L along the 1D line, or infinity outside of that region. And let's draw it. So when we say the potential is infinity here and here, this really just means that the particle can't exist there. So our boundary conditions take a slightly different form this time. We have that the boundary condition, the wave function at position x equals 0 and at position x equals L must be equal to 0. So we're no longer looking for the wave function to be continuous between the regions. We use the fact that the wave function must vanish in these two regions here, and so must vanish on the boundaries of those regions. So within the well itself, where we want to solve for the particle, we have the potential equals 0. It's still a constant, so we're going to have our plane wave type solutions. But in this case, we're going to be considering standing waves rather than travelling waves. So the solutions look like this. Cos and sine. And we can apply these boundary conditions. I've labelled them both 1 because they're kind of taking the place of what used to be condition 1. Let's call them condition 1 and condition 2. This one and this one. So applying those boundary conditions to this state, boundary condition 1 tells us that phi of 0 equals 0. So if we stick x equals 0 into here, this one disappears anyway, and we find that 0 equals a. And using condition 2, we only have b sine kx left. We stick x equals L into it, find that it must equal 0, and so we need sine of k L equals 0, and so we find that kl equals n pi, where n is any integer. So let's label those k's by that integer n, and our solutions to the for the Eigen Energies are as follows. H bar squared k squared over 2m, but where k is now labelled by n, and we can substitute this expression in here for kn. So this equals h bar squared over 2m, brackets n pi over a all squared. So, and let's label the energies by that integer n as well. So we have an infinite tower of different energy eigenstates which solve the Schrodinger equation in the well, given by this expression here. For each, there's a corresponding eigenfunction, so these are the energy eigenvalues that solve the time-independent Schrodinger equation, and our energy eigenfunctions we've solved for here. Let's just rewrite this equation, taking these two things into account. So this is our time-independent solution, the solution to the time-independent Schrodinger equation. As always, we can add back in our time dependence very easily for the energy eigenvalues, and in fact, if we do that, remember we write the time-dependent wave function as psi rather than phi, and we can update this as follows. So when we add the time dependence back in, we can also label our energy eigenstates by n, or energy eigenfunctions. We have the time-independent form multiplied by our winding phase factor e to the minus IEN t over h bar, where En are the energy eigenvalues. Okay, so let's plot those solutions on the next board. So we'll just move this up to the corner. So for n equals 1, we have this form. We've plotted the modulus of psi1, which is time-independent. Similarly, psi2, with a node now in the centre, psi3, and so on, and each additional, as n increases, we increase the number of nodes in the well. If we plot the potential again over there, it's conventional to plot these energy eigenfunctions on this plot. Now, of course, that's slightly incorrect because the y-axis here is the potential, whereas the y-axis over here is the modulus of the wave function. Even worse, we sometimes like to write what we write down as psi without the modulus sign on it, which would in this case come through down like this. But of course that's not really accurate, because psi without the modulus is a complex number, and we have this complex winding. So what you might prefer to think, if we take the example of psi2, for example, and rewrite it, we might like to write something like this, where we've drawn a sine. But as that complex phase winds, this can of course switch through to this solution, into negative sign. But in general, actually, what we really have here is the real part of psi plotted here, and we have another axis coming out of the board at 90 degrees, which is, say, the imaginary part of psi2 in this case. And really what happens is that this original wave function winds around the axis in the complex plane as it evolves in time. Okay, all that taken into account, we can plot the psi1 over there, psi2, where this is kind of a snapshot of the complex wave function where it happens to be purely real and the positive value. If this distance here is 1, so the height of this would be E1, and the height of this one would be E2. Again, this is all really conventional. The energies can be separated according to potential. They have the same units. But the form of the wave function doesn't really fit on this plot. And finally, psi3, where again, I've drawn a snapshot of this where it happens to be real. Now, I'm partly showing this just because this is so common to show these things that you'll see it in textbooks and on Wikipedia, for example. But it's slightly sloppy notation, but hopefully one that's nevertheless quite intuitive. Okay, so in the next video we're going to take a look at some properties of these different energy eigenfunctions that solve the problem. In particular, they're a form of what's called a bound state. So all these states are bound into the well. There's an infinite number of them. When we call it a well, even though it's above 0 in terms of potential, you can think of it as, well, we can just shift down the infinite parts down to 0, and this is an infinitely deep well with an infinite number of these energy eigenfunctions in it, each with their own energy eigenvalue. Okay, thanks for your time.